Hi students, today we are going to derive an expression for the self-inductance of a solenoid. So the symbol for the self-inductance of the solenoid is capital L. Now for that I have considered a solenoid having total number of turns capital N and total length L. Small l is the length of the solenoid. So these are the terms we are supposed to write below the diagram. Capital N represents the total number of turns. Small l represents the length of the solenoid. And if you divide capital N by L, that ratio is denoted with the symbol small n. So small n is called as turns density. So which means the number of turns per unit length. And capital A is the area of cross section of the turns. You can see here, these are all the turns, the circular turns. Each circular turn is having the same area A. Since this is carrying a current I, it is a current carrying solenoid. So we have already studied that when a current carrying solenoid is placed in air, it behaves like a bar magnet. We have already studied when it is suspended. So there will be magnetic field along the axis of the solenoid. You can see the magnetic field lines are represented here. These magnetic field lines are found to be uniform along the axis. Outside the solenoid, the field lines will be curved. And if it is an ideal solenoid, of course there is no magnetic field outside the solenoid. So where is the magnetic field of the solenoid present means it is inside the solenoid and along the axis of the solenoid. So you can see here this direction of the magnetic field B. B is a vector and it is pointed from left to right. And the area of each circular turn is associated with the magnetic field and hence area is also a vector. So that is denoted by A. A is the area of the circular turn. And since it is a vector, how will you find the direction of the area vector? By drawing a unit vector perpendicular to the direction of the plane area. So you can see here, if you draw a normal to this plane surface, that is also pointed along the direction of the magnetic field. So the area vector A and the magnetic field vector B both are in the same direction and hence the angle between the A vector and the B vector is equal to 0. So I am going to write here theta, the angle between the area vector and the magnetic field vector is equal to 0 degree. So these are all the first understanding of the coil. Now we are going to derive the expression for the self-inductance of the solenoid. Okay students, if B is the magnetic field, if this capital B is the magnitude of the magnetic field along the axis of the solenoid, we have already studied that the expression for the magnetic field along the axis of the solenoid. So magnetic field due to the or along the axis of the solenoid. Along the axis of the solenoid is given by B is equal to mu naught into small n into I. So this is the first equation we should remember. So I have written this in the scalar form. Magnitude of the magnetic field B along the axis of the solenoid is equal to mu naught times n into I, where mu naught is called the magnetic permeability of free space. Okay, now you can see here these each and every turn of the solenoid is associated with the same field only. So same field only is linked with each and every turn. And also these lines, magnetic lines are also called with the name magnetic flux. You see here, there are some magnetic lines. See 1, 2, 3, 4, 5, 6, 7, 8. So many number of lines are there. That is called the flux. Phi B for magnetic flux. So phi B is the magnetic flux linked with one coil. Okay. So I am going to write the expression for the magnetic flux. Okay. Magnetic flux linked with each turn, linked with each circular turn. Okay, it is given by phi B. Phi B is a symbol for the magnetic flux and it is a scalar quantity. It is a dot product of these two vectors. So you can see, for example, this is equal to the closed integral, okay, the closed integral of a B vector dot product, the area vector. dA is a small area associated with each turn. So this is closed for the area. So this is a area integral. So integral B dot dA. So this is now equal to, this is once again equal to integral B into dA is nothing but the area A into cos of 0 degree, cos of theta. So cos 0 is equal to 1 and this is equal to integral of B into dA. Actually this is B into dA, so that B into integral of dA will be equal to what? This is equal to B into A. Okay, so integral of dA is equal to the area of each term, that can be written as what? B into A. So this is flux phi B is now equal to B into A, which is once again equal to, substituting for B from the first equation, it is also equal to mu naught N I into A. So this is the second equation for the flux phi B linked with one turn. So like this, for one turn we have written the expression for the magnetic flux. So there are totally how many number of turns in the entire coil is capital N. That is the next step. Therefore, the flux linkage. What do you mean by the flux linkage? The flux linkage is defined as the total magnetic flux linked with all the turns. For one turn we have written equation 2. Therefore, for n number of turns, that is called the flux linkage. Okay, that is now equal to n times capital N into phi B. So this is capital N times phi B is the total flux linkage with the entire solenoid. So I am going to multiply this equation N and 2 by capital N. So this is equal to now capital N into mu naught into small n I into A. But you can see here n by L is equal to small n. Therefore, shall I write that capital N is equal to small n into L? Shall I substitute? I am going to substitute. This is now equal to small n into L into mu naught N A, and then I will write I separately here, the current flowing through the solenoid. So this is now equal to, first I will write the constants in proper order. So mu naught is written first, then n into n becomes n square, then comes the area A into L, and then followed by this current I. So this is a flux linkage. So this is considered to be the third equation. Have you understood? So the flux linkage N phi is equal to mu naught N square A into L into the current I. Okay students, from the definition of self-inductance of a coil, we have already studied that this flux linkage N into phi B, this flux linkage is proportional to the current I flowing through the coil. Is it not? How much flux is linked? You see the flux is linked here, that is because of the current flowing through the coil. So the flux phi depends on the current I, or N into phi B is equal to a constant L into I. This is equation number 4. Okay. So the flux linkage also is equal to L into I. Now you look at equations 3 and 4. You equate on the right hand sides. So equating, that is from equations 3 and 4. I am going to equate the right hand sides of the equation. So L into I is equal to mu naught N square A L into I. Now the term I can be cancelled on both sides. So we get the final equation. Therefore, L is equal to mu naught N square A into L. So this is the last and the final equation number 5 for the self-inductance of the coil. Right side is mu naught. Mu naught means what? The magnetic permeability of free space. So inside a solenoid, free space is present. Suppose if you keep a soft iron bar inside the solenoid, means we have studied in the earlier class itself that the magnetic field strength will increase. Is it not? So I am going to place now some other material, okay, like soft iron. So if any material medium, okay, is placed, if any material is placed, this material should be magnetic material. Usually we keep ferromagnetic material like steel, soft iron, simply iron, like that. Okay, students. So if any material is placed inside the solenoid, then L is now equal to mu R times mu naught N square AL. Okay. So this is another equation, if you want you can say, for solving numerical problems. So L is also equal to mu R times mu naught N square A into L, where mu R. So mu R is now equal to mu divided by mu naught, and this is called as relative permeability. So this is relative permeability. These are all we have studied in the theory, okay, earlier, before the derivation itself. So this is relative permeability of the medium. Okay, students, have you understood? Okay, fine.